the column construction material, preferably it is the stainless steel, but along with the stainless steel, glass, aluminum, copper and PTFE, these are the other choice materials. But amongst all those, the fragility of this column made up of stainless steel, that is best, that is least fragile than the column which is made up of stainless steel. It is less reactive with all the molecules which are present in that, which are going to be present in that complete reaction vessel or reaction container. So stainless steel column it is preferred. So we have discussed about the length of analytical and preparative column. So analytical column, it is having smaller length than that of the preparative column, and that is 20 to 50 centimeter, whereas the preparative column, it is having the length that of the comparatively which is larger in size. So diameter, internal diameter, it is not variable in case of both the things, that is 1 to 4 millimeter. The more the diameter, the more the lateral diffusion that will be seen, and that's why the internal diameter is not that much big, but the length of column that is increased in case of preparative purpose. The packing material, it is supported by a porous stainless steel or Teflon disc at the end of column, so that it will not get leak out from that column itself. Then what is the important column packing materials which are mostly used? So maximum separation without or with minimal band broadening, it is the function of stationary and mobile phase which is chosen. So the coarse material which if you use, the area which is available, which is made available, that is found to be reduced. If you use more fine material, that means the particle size if you reduce, then you will be having the higher amount of surface area with it. So you have to adjust along with the surface area, that means the particle size and the solvent system and the pressure. So these three things you need to manage, and accordingly you have to manage the flow rate of the solvent system which is flowing through it. And in order to manage the flow rate, what you have to manage, you have to manage the complete pump, or that means the pump pressure which is going to be exerted on that liquid. So three important forms of column packing materials they are considered. Rigid solid rather than the gel structure, it is mainly used. It is a dry powder or dry material which is filled inside the column, and it is equilibrated with the solvent system of the typical standard operating procedure. So three forms they are considered. The first is microporous support, second is pellicular support, and third is bonded phases. So what is this microporous support? Where the micropores they ramify through the particles. So the particles, their arrangement, they will prepare a microporous structure, and they usually they are of 5 to 10 in diameter. So you need to consider the example for this. So this is the way the diagram it is being shown over here. The diagram it shows how the particles they construct the micropores inside. Okay. Second is the pellicular support. It consists of solid inert core onto which the several pore particles, that is the glass beads or of different or the particular diameter, they are coated on that. So this is the way how that B type, that means the pellicular support that is being seen. This is the inert core, and on this inert core the particles or the glass beads they are coated on that. So that is the way how the second type of column packing material it is seen. And third is bonded phase, where the stationary phase is chemically bounded to an inert support. So this is the way how silica bead it is chemically bounded with the stationary phase. So the leaking, the problem of bleeding of column, it is minimally seen in case of bonded phase, whereas it may be seen in case of thin layer, that is the coating or the pellicular, or in the micropore structure as well. But it is not seen, or it is least seen in case of bonded phase. Even in case of micropores, the bleeding of column it is least seen, but comparatively bonded phase it will give you the best result. But the for some certain biomolecules also you need to have this pellicular type of structures. So it again it depends on the type of column and the procedure, that is the optimized procedure, that what type of column material form you will be using. So this is all about the column and column containing column material of construction of that column, and about the column packing forms. We have discussed different column packing materials in our previous lecture. Now comes the detector. What is the detector which is used inside? It mainly it may be a detector which detect depending upon the characteristic, or it may be the detector which considers some other forms. So UV visible detectors majorly or mainly they are used. Then these detectors are they are inexpensive, they are sensitive, they are normal flow. If you consider, that means that of the solvent, then they are insensitive for that. So they don't get fluctuated even after the alteration of pressures. So temperature fluctuations also they withstand, and they are suited for gradient illusions as well. So UV visible detectors, they are mostly used detectors in case of HPLC. But again, the standard operating procedure for each and every molecule, that is that is considered to be variable for all the processes. So the spectrophotometers which we are which are attached to this UV visible which are attached to this HPLC, they range from 200 to 800 nanometer in majority of UV detectors. And advantages, if you consider, the biological substances can be detected by these appropriate wavelengths. And apart from the above two, refractive index monitors and fluorescence detectors, they are also available and mostly used in the case of HPLC. So we will be discussing all these detectors one by one now. Considering this is the detector, bulk property and solute property detector, as we have discussed. These are the examples of detector, and the range, the sensitivity and availability that is compared in this table. This is for your information. Then absorbance detector, that is the UV detector, how it is visible or how it works basically. So this is the way how the from column the input it comes inside. This is the UV source, and through this UV source, UV light, it is bombarded. This is the quartz window. Quartz window won't allow any holders noise inside that typical vessel, so that only the absorbance of that sample material that is being considered. Even you can minimize the solvent system's absorbance by adjusting the variables. Okay, so the UV it passes through, and detector it records the absorbance, that is lambda max. And due to this, and depending upon that, quantitative as well as qualitative analysis can be done. So this is the way how UV type of detectors they work. I have given a short note as well along with this for your notes purpose. So you need to read this, and then you have to add your own reading points and whatever I have discussed in the lecture in that typical section. So that is the way you will be preparing your notes. Then along with UV absorbance, some of the instruments, they are also having infrared absorbance detectors. Okay, so two types you can consider. First, depending upon far IR and near IR. Okay, so there are two different ways how you can consider the IR spectrum or infrared spectrum as an detector for that typical system. Then next is the fluorescence detector. Fluorescence is observed by a photoelectric detector located at the 90° to the excited beam. So this is the way how the detector it detects the fluorescence which is caused by that typical instrument. The simplest detector employ a mercury excitation source. What it employ? A mercury excitation source and one or more filters to isolate the bond of emitted radiation. So the phenomenon of fluorescence it is used, and the phenomenon of fluorescence, it is the typical characteristic feature of individual compound, and that's why this typicalness it is used as the basic concept for that individual material. Okay, so the advantage for this system is the highest sensitivity. Okay, so the highest sensitivity that is important in case of any detector, the least amount that is very important in case of a biological sample if you are analyzing. Okay, so the analysis, whatever the biological sample you are going to analyze, it will be present in picograms or fematograms in your sample. So you need to detect it, and that's why it is considered that the detector which is there for the HPLC, that must be highly sensitive. So for that reason, fluorescence detectors they are used for the samples which are in very less amount. That means in that sample, your biomolecule, your interest biomolecule, it is present in the negligible amount, but still you want to detect it, you want to estimate the quantity of that, and that's why for those protocols, fluorescence detectors, they are the choice detectors which are used. Then refractive index detectors. So refractive index is also a typical Coefficient you can consider, which is like an melting point or boiling point. Refractive index, that is also an constant term which you can use. So again, they are used in the case of this HPLC detectors. They have the significant advantage of responding to nearly all solutes. So as melting point and boiling point, it is available for each and everything like that. This is the physical parameter you can consider with which the you can identify and detect the biomolecules. So all the biomolecules you can consider, all the solutes, they can be estimated using the refractive index or RI detectors. So it is the general detectors basically, and analogous to flame or thermal conductivity detectors in GC. So you need to burn it. You need to burn it in case of GC, whereas you need to determine the refractive index in the, when you are dealing it with in the HPLC and the refractive index detectors you are using. In addition, they are reliable and unaffected by flow rate. Okay, so this is another advantage you can consider for the refractive index detectors. They are, however, highly temperature sensitive. That is an issue for this type of refractive index detectors, because the matter of state that gets altered due to the temperature which is being considered, and constant temperature for that is been very important, that you need to maintain the constant temperature till the detector it detects the substance which you want to detect. They are not as sensitive as most type of detectors. So that is an disadvantage you can consider for the refractive index detector. Then comes the electrochemical detector. These work upon amperometry, polarimetry, coulometry, and conductometry. So again, it depends upon the electrochemical terms which you need to consider. So amperometry means depending upon the fluctuation in the amperes. Polarography, then coulometry means temperature alteration you can consider. Conductometry, that means the conduction of some electrochemical parameter you need to consider. So again, they are having high sensitivity, but they are also having the simplest mechanism, but still the highly employed detectors for HPLC, they are still RI or fluorescence or UV visible type of detectors. Okay, so these are the different detectors which we need to consider. So this is all about the detectors which we need to consider. And the last detector, that is mass spectroscopic detector. Here mass spectroscopy it is employed. We will be discussing this mass spectroscopy detector when we will be discussing mass spectroscopy in our next unit. So remind me to discuss this detector at that time as well. What exactly is the important part of this mass photometric detector? This mass photometric detector, it is highly sensitive, no doubt. It works upon the splitting of the typical molecule and the parent molecule and daughter molecule pattern which has been created, that is being considered as an output. So this is also a good type of detector which is used in case of HPLC output. Okay. So with this we have completed the line diagram and instrumentation of all the systems which we can see in the lab, that is the HPLC. Now there are two variants of HPLC which we need to consider. The two variants, they are reverse phase and normal phase. So these two variants, reverse phase chromatography, that is the syllabus heading for you people in your syllabus. Okay. So that reverse phase is not a different type of chromatography, but it is a variant of HPLC itself. So what exactly it is? Reverse phase and normal phase, these are the forms how the packings they are being performed.